Let's continue with the heart. The question that this mini lecture addresses is what happens when the heart beats? And in particular, we're going to consider how the muscles are activated in the heart, how that results in pressure elevation in the chambers, which drives blood flow. So here's a schematic of the heart from its exterior, where we can see the atrium, the ventricle, both the right heart and the left heart superficially. And if we were to dissect open the heart, then it would reveal those chambers, something like that. And now what we're going to do with this schematic is step through the major events of muscle activation in what's called the cardiac cycles. The cardiac cycle are that refers to the periods of time that the muscles are activated and then relax over the course of a heartbeat. So we're going to begin with the atria. And I might use the singular atrium or atria because both sides of the heart essentially do the same things at the same time. Same thing for the ventricles. Okay, so first we begin with the period of contraction for the atria. All right, that period of contraction is called atrial systole. The word systole refers to a period of time where the cardiac muscles are activated to contract. So atrial systole, we've already established in the last lecture that the atria function to help fill up the ventricles. And so the muscles around the atria are activated for that purpose, and then they create an elevated pressure. The blood, being a liquid or a fluid, will tend to move from high to low pressures, and at the same time the AV valve opens up on both sides. So there's an AV valve. This is the direction of blood flow because of that elevated pressure that we have in this case in the right atrium, same thing on the left side. So what we're going to do on the bottom of this slide is track these events over the course of time. So we have the atrium undergoing this period of systole activation. Now the ventricles, of course, also are activated. And so that brings us to early ventricular systole. Now the elevated pressure in the ventricles serve to create high pressure in those chambers. And we've added the ventricle here to our timeline, and we're particularly focused on the early events of systole. So the muscles there are activated. That elevated pressure serves to shut the AV valves. And early on in ventricular systole, the semilunar valves through which the blood will eventually flow have yet to open. They're pretty stiff valves, and so the pressure has to rise enough to open up those semilunar valves. And that's what we see as we transition over to late ventricular systole. So the muscles are still activated, that elevated pressure opens up the semilunar valves, and as a consequence, we have the blood flowing from the ventricles into these major vessels that leave the heart. So in the case of the left heart, that major vessel is the aorta, so the blood flows into the aorta, whereas we have the pulmonary artery serving as the major vessel that leaves the right heart. So those are the periods of contraction for the two chambers of the heart, but the periods of relaxation are important as well. So we have atrial diastole. Diastole refers to a period of relaxation. And at this time, the atria fill up with blood. Okay, so we have, in the case of the right heart, the vena cava, the major veins that we have the inferior and the superior vena cava, the major veins that fill up the atria. Okay, so you can see atrial diastole is a pretty long period of time compared to that period of systole, and the atria are filling up with blood the whole time. Okay, early ventricular, then there we have the blood flow on the schematic. Early ventricular diastole is characterized, so this is at the end, the ventricles have contracted and now they begin to relax. So we move along on our timeline and we initially have a closure of the semilunar valves. So schematically this is shown with them open. We advance through time. Now they've closed. And the ventricles will essentially, okay, so after contraction, the muscles are at their shortest length. The connective tissue surrounding the contractile cells is very elastic. And so immediately, as the muscles relax, you have the ventricles expanding just passively. This is before the atrium begins its contraction. You just have this passive expansion of the ventricle. Now recall to our last lecture how we can simulate the effects of expanding the volume of a chamber in the heart with a syringe. And if you pull on the plunger of a syringe, you're expanding the volume on the interior of that chamber. So just imagine if that expansion is driven passively, it's still an expansion and it's going to create a relatively low pressure. So as we have the walls of the ventricles expanding in this way and creating a low pressure, there is now the opportunity for the AV valves to open up and allow blood to flow from the atria into the ventricles. Okay, so when we look at late ventricular diastole, the AV valves have opened and the ventricles are filling. Okay, now note, this is occurring without any contraction of the atria. So the blood begins to flow during this period of dual diastole, and then as the next heartbeat begins, that's initiated by atrial systole. The ventricles are still relaxed. We can see that the atrium, when it contracts, essentially tops off the blood that flows into the ventricles. So it flows passively initially. That's what we're looking at here for this point in time. And then eventually the atria actively fill the ventricles. All right, now let's look at physiological metrics of the cardiac cycle. And we're going to continue with the timeline that we see down below, but we're going to instrument a heart and make recordings in the chambers. And we're going to focus on the left heart. So we have those parts highlighted here. Okay, there's the left atrium, the left ventricle, and the blood that flows into the aorta leaves the left ventricle through that semilunar valve. And we're going to first instrument the two chambers with a pressure transducer. So during atrial systole, the ventricle pressure is quite low. This is not surprising because the muscles are inactive in this point in time. The atrium is active. The atrial walls are much thinner than the ventricular walls. So the total pressure that can be generated in the atrium, even when the muscles are activated, is not particularly high. So when we look at the pressure in that left atrium, we see it is greater than in the ventricle, but not dramatically greater. And you can contrast that to the pressures that are generated by the ventricle during ventricular systole, which we see just sort of skyrocket and much greater in magnitude. Now, of course, during ventricular systole, the atria are relaxed, and so there is a drop in pressure, like that. You have the same phenomenon once the ventricles stop contracting and move into ventricular diastole. And then we see a similar low pressure in the atrium as it continues diastole. Now, perhaps the most interesting aspect of pressure has to do with what occurs in the aorta. The aorta has always a relatively high pressure. Even when the ventricles are relaxed, so ventricular diastole here, the aorta has a much higher pressure than the ventricle, or the atrium for that matter. Now we're going to leave it to a future lecture to explain that elevated pressure. So we're going to leave it as a mystery for the moment. I'll tell you that this is not created by muscular contractions. Nonetheless, it's a high pressure. Now, in order for the blood to flow from the ventricle into the aorta, the pressure needs to be less in that vessel. And that's indeed what you find during ventricular systole, is that there's a lower pressure in the aorta than in the ventricle. Okay, at the end of that period of contraction, you have the drop off and ventricular pressure, but the aorta stays high. Now, if we monitor the changes in the volume of the left ventricle, then we get probably what you would expect. So here we have left ventricular volume. During ventricular diastole, as the atrium is contracting, so this is, I should call it atrial systole, then we have the blood squirting from the atrium into the ventricle. So not surprisingly, the volume increases. Then during ventricular systole, as the blood clears that chamber, then not surprisingly, the volume drops. And then, as I mentioned, during this period where diastole is occurring in both chambers, we have blood flowing from the atrium to the ventricles, and that is reflected in the volumetric changes of the ventricle. This kind of diagram showing us pressures and other physiological measurements as they relate to systole and diastole is known as a Wigger's diagram. Now, one thing that's interesting about the Wigger's diagram is that if we understand when the valves are open and closed, then we can infer blood flow because we know that that fluid will always move towards low pressure. So, for example, during atrial systole, we know that the AV valve is open, and we can also see here that the atrial pressure is greater than the ventricular pressure. And so we can infer that we have flow from the atrium to the ventricle. Now you might have noticed these little blips in the pressure traces. That corresponds to a change in the state of a valve. In the case of that little blip that we see in the atrial pressure, that corresponds to a closure of the AV valve. When you look at the aorta and its little blip here, that corresponds to an opening of the semilunar valve. Now, once we know that that is open, and I mentioned earlier that during early ventricular systole, you have to elevate the pressure in order to drive that opening of the semilunar valve. And so that's what occurs right in this period of time here. Once the valve has opened, now blood can flow. And again, not surprisingly, we see a higher pressure in the ventricle than in the aorta. So we can infer that the blood is flowing into the aorta from the ventricle. We get another closure of the semilunar valve reflected in the pressure in the aorta. And we also have an opening in the AV valve reflected in the atrium pressure here. Now, once that occurs, now blood can flow towards lower pressure. That low pressure is in the ventricle. Another important physiological diagnostic are the sounds made by the heart. Okay, whenever you go into the doctor's office, the doctor will pull out the stethoscope and monitor your heart sounds. What generates those sounds? Well, here we see an example of the heart sounds. And we can listen to this sound. So the first sound corresponds to the end, or it correlates with the end of atrial systole, and the second sound correlates with the end of ventricular systole. So the boom, it's boom. You've got the higher or the louder sound occurring second in that sequence. The first sound is generated by a closure of the AV valve. And we have that event here, and the sound correlated with that. And if we look at an ultrasound of the AV valve, then the sound is generated when you have a clasping together of those two parts of the AV valve. Okay, so when they're open, they sort of flap as the blood is rushing by, and then that closure is what's generating the sound. You have a similar sound generated by the semilunar valve, and that's what we see back here, where you have this sort of clasping of hands. As they clap together, the sound is generated, and that corresponds to this closure here, which I failed to label, of a closure of the semilunar valve, corresponding to that sound. Now, another really valuable diagnostic comes from an electrocardiogram, which is a gross metric of electrical activity in the body that is generated by the heart. And there are various forms of what's called an ECG. The ECG, in its simplest version, requires only 3 surface electrodes. And then by making comparisons of the changes in potential at those 3 points, then you can get this metric of electrical activity that looks like this. So we're going to add that to our timeline here. These little blips are characteristic of a healthy heart and the electrical activity generated by that healthy heart. Each of those little blips is categorized in an alphabetical sequence. So the first blip is what we call the P wave, and that's followed by this complex here called the QRS complex, which is followed by the T wave, and then we have the beginning of another P wave. So the ECGs function to allow us to monitor the activation of the atrium and the ventricles, and in particular the muscle activity in those chambers. Now, I've bold-faced the word change here because the ECGs do not reflect the membrane potentials. In fact, in this point in time, the atrium has an elevated membrane potential. All the muscle cells in that chamber actually have a very high membrane potential, and we can see that there's just a flat curve there. But the P wave marks the beginning of that electrical activity, and the Q corresponds to the ending of that electrical activity. So you can think of the ECG in part as reflecting the first derivative of the membrane potentials, or the change in potentials, both depolarization and repolarization of the musculature in the 2 chambers. So let's track how the ECG waves correspond to the electrical activity. So we're going to focus in on the heart. Again, we've got the atrium and the ventricle highlighted on the right heart. And what we're going to add here are the autorhythmic cells. Now, I've described them before. You know that they're capable of generating spontaneous electrical activity that serves as the pacemaker for the heart. Those autorhythmic cells are localized in very particular regions of the heart. So altogether, they form a network that looks something like this. The first bundle of autorhythmic cells is known as the SA node. Okay, so the SA node is a bundle of autorhythmic cells that initiate a heartbeat. So the SA node really drives the beat of the heart. And from the SA node, via gap junctions, there is a depolarization wave through the contractile cells. But there's also a transmission of action potentials via internode fibers. Okay, so you can think of them as sort of an expressway of action potentials that travel from the SA node more rapidly than the wave of depolarization that travels through the musculature. The internode fibers terminate at what's called the atrioventricular node, or AV node. So the action potentials via the internode fibers drive the action potentials in the AV node. The AV node has, just like the SA node, autorhythmic cells that are capable of autonomous activation, but the period of time, the period between action potentials, so that would be the period of the pacemaker potential, is long in the AV node. And what the SA node does is effectively drive the autorhythmic cells in the AV node to threshold earlier than they would be if the AV node cells were just in a dish on their own. So it's for that reason that the SA node drives the activity of the AV node. So as you become more active and your heart rate increases, just imagine that the SA node starts increasing the frequency of its activations. That in turn drives the AV node to a higher frequency. Now the AV node then transmits action potentials for the ventricular musculature. And that occurs via, there are a variety of fibers, but the ones I'm going to highlight are called Purkinje fibers. So imagine an action potential traveling towards this end of the heart. This is called the apex of the heart. And then you have a wave of depolarization that propagates back upwards. Okay, so those fibers allow for the transmission of action potentials from the AV node through the ventricular musculature. So let's step through the ECG to see how this all works. First, we have the P wave, and that corresponds to the depolarization of the atrial musculature. So we have a little schematic there, and just imagine there's this wave of activation in the atria. That's what the P wave designates. So when the ECG is flat during atrial systole, you can imagine that the musculature is fully activated and there's no change again until we have a repolarization or a turning off of this activation in the atrial musculature. Now the QRS complex is in part reflecting that repolarization, but also a depolarization of the ventricular musculature. So we have this transmission of the depolarization through the Purkinje fibers that then floods through the ventricular musculature, so that in this period of time between the S and the T waves, when the ECG is flat, the ventricular musculature is fully activated. Again, ECGs reflect changes in electrical activity, not the current state in electrical activity. So we have a flat period of time here for the ventricle when it's fully activated, and here for the atrium for the same reason. We also have this flat curve when there's no activity, and there's no activity because both chambers are undergoing diastole here. Okay, so we've got flatness in all three cases for three different reasons. Then the beginning of a P wave is initiated by the SA node, and we see that continue on the beginning of this chart. Okay, so the question that we set out to address was, what happens when the heart beats? And we've considered the muscle activation. We had the timing of SA and AV nodes driving that muscle activation. Action potentials propagate through fibers and through the contractile cells. This creates changes in pressure. In particular, we have systole in both chambers of the heart, driving blood flow from those chambers. In the aorta, we have this mysterious elevation of pressure during diastole for the ventricle. So what is that about? That's going to be addressed later. It's just an important observation at this point. The blood flows towards lower pressure if permitted by the valves. So the valves control the direction of flow, as do differences in pressure. And the flow is predictable if you know what the pressure is in the different chambers and vessels, and if you know what the state of the valves is. And by states, I mean whether they're open or closed.